So this is a lesson about infinite series, and the first type of series we're going to consider are alternating series. So in alternating series, you have numbers, an, which are positive, and they are decreasing. So an is greater than or equal to an plus 1 for all n. And a series looks like the following. Sum, let's say n goes from, say, an, and goes from 1 to infinity. But we're not just summing the numbers, they have to alternate in sign. So this is minus 1 raised to the power n minus 1. So our series looks like a1 minus a2 plus a3 minus a4 plus, and so on. That's so they're alternating in sign. And let's see. This is an alternating series. It's an infinite series. So let's take a simple example. Suppose we take, let me write it as a function. N goes to 1 over n. I'm writing this as a function a of n. And now, this is the infinite series. Because it doesn't give us the answer. This summation, when you write with a capital S, writes out a mathematical form, the infinite series. If I copy this, but write it with a lowercase s, so this is sort of magical. The alternating series, summation minus 1 to the n minus 1, it converges to log 2. What happens if it's not an alternating series? Suppose it were the series where we just sum the terms an. It diverges. So the sum of this is the harmonic series, summation 1 over n diverges, but this alternating series converges. Suppose I let an be n squared, 1 over n squared. What does the alternating series converge to? Pi squared over 12. Suppose I took an to be square root of n. What is the sum of the alternating series? Ooh, this just means it's too complicated to write down. If there's something called the polylogarithm, that's what this is, but there's no way for us to express it. But if I want to know what it is numerically, I could just evaluate this as a decimal, and this is 0.604. Now, what is the partial sum of the series? That's sort of interesting. So suppose I take the series not from 1 to infinity, but just the first capital N terms. Let's say maybe let n be equal to 10. Let me make it easier. This is a nice example, 1 over n. Now, so this is the sum of the first 10 terms of the alternating series. So this is, what is this? This is, if you were to write it out, it would be 1 minus a half plus a third. In fact, let me just do it. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus a ninth minus a tenth. Right? That's exactly what this is. Right? It's alternating in signs, and in absolute value, the terms are strictly decreasing, and the limit is 0. Now, it's interesting to make the following comparison. This is the sum of the first 10 terms of the series, and this is the infinite series. Suppose we compare the two. So that's the infinite series minus this, which is the sum of the first 10 terms. What is that? Well, that's what it is. But let's try to know what it is exactly. Let's write it as a decimal. And the beautiful theorem about alternating series tells you the following. So suppose we let S be the infinite series. And suppose we let S n be the finite series, the partial sum of the first n terms. Oops. Let me write this as capital S. Yeah. So this is the infinite series. This is the first capital N terms. This is the difference. Let's see if I can evaluate that. Just curious why it doesn't want to give me this. So let me do it differently. So this is the sum from 1 to infinity. This is the sum from 1 to 10. That's the difference. So the important theorem about alternating series tells us that if you take the S as the infinite sum minus the partial sum of just the first n terms, and you take the absolute value of that, because it can be positive or negative, that's always less than the nth term of the series. So what does this say? Let's just look. So S is equal to the infinite series. Well, actually, I don't even need that. So here we have, this is the series from, this is the infinite series from 1 to infinity. This is the sum of the first n terms. This is going to be less than an plus 1. Now, in this case, an is 1 over n. So what this says is that this difference is less than 1 over 11. Let's see, how can I write this down? I don't know if Maple will allow me to do this. Yeah. So this is the infinite series minus this partial sum of it. This is what we get. So let's do the following. This is interesting. For n from 1 to, let's say, let's go up by 20. From 10 going up by 10 to 200, do. And what I want to do is take the infinite series minus this partial sum and compare it to 1 over n plus 1. So in each case, the right-hand side has to be bigger than the left-hand side. And it is. This is a kind of a demonstration of the validity of this theorem in Math 176 about the alternating series. Okay. It's interesting to consider some other very nice alternating series. For example, the sum of minus 1 to the n minus 1 over, suppose we go through the odd numbers, 2 times n, oops, 2 times n minus 1, as n goes from 1 to infinity. So this is the alternating sum of the reciprocals of the odd numbers. And what is that equal to? Wow, now that's amazing. So this infinite series converges to pi over 4. That really is quite remarkable. Yeah. Here's an example which might have been homework in Math 176. I don't know. Suppose we take the alternating series 2 to the n times n factorial. 2 to the n times n factorial. I should remind you that n factorial this is the product It's the product of the integers from 1 to n. That's what this is equal to. That's curious. Okay, let's start at 0. Perfectly okay also. I like to start with the positive terms though. 1 over the square root of e. Huh. Suppose I make this 3 to the n. Yeah. Why is that? Well, you can figure out why that is if you, well, sooner or later at least. Okay. So now we're going to consider the ratio test. The ratio test says the following: if you have an infinite series, it converges if the ratio of consecutive terms has a limit strictly less than 1. It diverges if this limit is greater than 1, and the test is inconclusive in other cases. So let's just look at a couple of examples. So suppose we let A be the sequence. A of n is six to the n divided by n plus 1 to the n. And we want to look at the series. Summation 6 to the n over n plus 1 to the n. So what we have to consider is a of n plus 1 divided by a of n. And what we really want to do is take the limit of this, then goes to infinity. That's what we want. Huh. The limit is 0. 0 is less than 1, so the infinite series converges. Actually, I should have put absolute value signs here. Okay. Let's look at another example. Suppose we take an to be four, 4 to the n divided by n squared. Does this series converge or diverge? So we look at this limit, the ratio of successive terms, and it's 4. 4 is greater than 1. So the infinite series diverges. And the third fundamental test for convergence is the root test. Root test says you take an infinite series and you look at the nth root of the nth term. So in this case, we look at the series absolute value of a of n raised to the 1 over nth power. So this is what we're looking at. And again, we're interested in the limit of this as n goes to infinity. Again, if the limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. And in other cases, we don't know. So let's look at, let's say, this last example. This is the infinite series. This is the limit we want to understand. And what we want to do is, let's compute the limit. The limit's 4. The limit's 4 is greater than 1. The infinite series diverges. So Maple is useful in many ways. Here you can actually have it do the work trying to implement the ratio test and the root test to see if a series diverges. And in the next homework, there will be some problems with infinite series. So that is the lesson.